Before we get started this morning, I'd like to welcome a special group of students that we have visiting us here today, Lake Burke High School in Virginia. Welcome to the Science, Space, and Technology Subcommittee on Space. Thank y'all for being here. Woke a couple of them up, I see. That's good. We haven't even got started yet. The Subcommittee on Space will come to order. Without objection, the chair is authorized to declare recesses of the committee at any time. Welcome to today's hearing entitled Searching for the Origins of the Universe, an update on the progress of the James Webb Space Telescope. I recognize myself for 5 minutes for an opening statement. The James Webb Space Telescope represents a significant investment by the U.S. taxpayer and holds the promise of producing revolutionary science that one day may rewrite textbooks. It could change the way we perceive our universe as well as our place in it. That is a lot to live up to. JWST continues the heritage of space-based great observatories, leveraging the accomplishments of the Hubble Space Telescope, the Compton Gamma Ray Observatory, the Chandra X-ray Observatory, and the Spitzer Space Telescope. James Webb will provide revolutionary astronomical measurements in the long wavelength, visible, and the mid-infrared range of spectrum. This will allow scientists to see light from the first stars, view the development of galaxies, and study the development of planets. The infrared range that the telescope will operate in allows the telescope to see through cosmic dust, view faint and dim targets, and observe phenomena such as redshift from the expanding universe. James Webb's unique vantage point from the Sun-Earth L2 is also an ideal location that will enable the observatory to make precise infrared measurements. The scientific returns from these observations will be compounded even more if James Webb remains on schedule and overlaps with existing observatories that continue to return significant science, or new assets such as the Stratospheric Observatory for Infrared Astronomy and the Transiting Exoplanet Survey Satellite that promise to complement James Webb's capabilities. This is enormous potential is balanced by the sobering history of James Webb's development, initially planned to cost $1.6 billion and launched in 2011. The program ballooned to a life cycle cost estimate of nearly $9 billion and slipped 7 years to a 2018 launch date. James Webb's history is well known, and I do not wish to open old wounds, but Congress would be complicit in any future delays or overruns if it failed to maintain proper oversight of this program. Despite the significant progress made by NASA and the contractors, the program is not out of the woods yet. It is now entering the critical integration and testing phase where unforeseen problems typically arise. These unplanned technical challenges could threaten the costs and schedule reserves during this critical period. Recent issues with the cryocooler, a critical component that is necessary for proper measurements, reinforces the need for persistent monitoring and oversight. The sheer technical complexity of this program demands it. Even after the telescope is fully assembled, shipped to Kourou, and launched into space, all of us will still be crossing our fingers that this massive spacecraft will arrive at its intended destination and execute its intricately choreographed origami-like deployment. Everyone involved in this project is working to make it a success. The engineers and technicians, the contractors, the managers and scientists at NASA, and even the members and senators here on the Capitol Hill. In 2011, the House of Representatives voted to cancel the program after its cost estimates skyrocketed and threatened not only other astrophysics missions, but also science mission directorate activities. The contagion of escalating costs even threatened other national priorities at NASA. Planetary science and even exploration programs have sacrificed funding to buttress James Webb and keep the program on track. With a statutory cost cap of $8 billion for development, Congress expressed both an endorsement and limitation. For the sake of all of NASA's programs, I hope that James Webb will launch in line with its updated schedule and current cost projections. Even after launch, issues related to James Webb will remain. For instance, what will happen to the additional funding poured into the Science Mission Directorate to cover James Webb's overruns? Will the astrophysics account maintain funding profiles consistent with these augmentations? Will the other programs and projects within the Science Mission Directorate return to their historical proportions after James Webb is launched? Will exploration programs recoup the funding transferred to the James Webb program, or will these proportions represent the new norm? With overall budgets remaining flat or only increasing marginally, how the other $600 million a year devoted to James Webb will be reallocated after launch is one of the most important decisions facing NASA and Congress. In light of decreasing budget requests from the administration for exploration, it may be appropriate to reconstitute the programs that sacrifice funding to cover James Webb's cost growth. Before I conclude, I would like to take the opportunity to thank GAO for their diligent work on the James Webb program. As the program matures, questions are shifting from whether or not the cost, schedule, and technical plans are adequate to whether NASA and the contractors are executing to those plans. I hope GAO will continue to provide this committee with insight into this complex program so we can all ensure its ultimate success. I also hope that NASA and the contractors heed the GAO's advice and recommendations. More specifically, I hope that in the future, NASA and the contractors will allow the GAO access to information and personnel so that they can fulfill their statutorily required task to monitor this program on behalf of Congress. GAO's recent report highlighted instances where their access was limited. Transparency and accountability are tenets of sound program management and oversight. I trust that won't be a precedent for future engagements. At this time, I now recognize the ranking member, the gentlelady from Maryland, for an opening statement.
Thank you very much, Mr. Chairman, and good morning and welcome to our distinguished panel of witnesses. Mr. Chairman, I want to thank you for calling this hearing to evaluate the development of the James Webb Space Telescope, known as JWST, and discuss the science that the observatory will enable. This hearing also comes at a fortuitous time on the eve of the 25th anniversary of the Hubble Space Telescope. And as an aside, I can remember when this exact same discussion, perhaps about the cancellation of Hubble, was part of the conversation in Congress. And thank goodness, 25 years later, looking back on that we didn't do that because of the amazing, amazing work that's been done and the learning that's taken place over the course of those years. But that was the conversation more than 25 years ago, and a good thing that Congress didn't take those actions. Launched in April 1990, Hubble was the first major optical space-based observatory orbiting above the distortion of the atmosphere and above rain, clouds, and light pollution. Many of today's younger generation have grown up with Hubble, and I dare say that most Americans have seen the awe-inspiring image taken by Hubble of the iconic Eagle Nebula capturing the famous pillars of creation. JWST is the next generation astrophysics observatory following Hubble. More capable and sensitive than Hubble, JWST is optimized to study infrared light from the universe, which will allow JWST to observe the first galaxies formed in the universe. In addition, JWST will see solar systems forming in our galaxy and possibly detect the presence of liquid water on planets around other stars, an indicator that such a planet may indeed harbor life. Mr. Chairman, that is exciting, and that is why I just can't wait for JWST to be launched and working. But I also recognize, as the Chairman has indicated, that the road to building JWST has not been an easy one. The observatory's history of cost growth and schedule delays has not gone unnoticed by the Congress. An independent review panel found in October 2010 that a substantial funding increase would be needed to complete the observatory. As a consequence, NASA rebaselined the project in 2011 with a life cycle cost estimate of $8.8 billion and a launch readiness date of October 2018. Congress indeed has done its share and funded JWST annually consistent with that rebaseline. We need to continue to do so. The Consolidated and Further Continuing Appropriations Act of 2012 directed the Government Accountability Office to report on the project on an annual basis. I appreciate GAO keeping Congress informed of that. With a launch now a little more than 3 years away and major integration tests looming ahead, NASA will be under pressure to demonstrate that it can meet the launch date with the cost estimate. And although the latest GAO report concludes that JWST remains on schedule and on budget, GAO also reported that, quote, technical challenges with JWST elements and major subsystems, however, may have diminished the project's overall schedule reserve and increased risk. At today's hearing, I hope to get answers on the following questions. What progress is being made in preparing scientific investigations and scientists who will capitalize on JWST's unique capabilities? And with 3 years until launch, what technical challenges and associated risks still remain? What steps are being taken by NASA and its contractors to ensure that the cost and schedule commitments are met? And finally, what is the level of confidence that NASA will be able to meet the October 2018 launch date? Again, I want to thank our witnesses for appearing before our subcommittee, and I do look forward to your testimony. And, Mr. Chairman, I yield back.
Thank you, Ms. Edwards. I now recognize the chairman of the full committee, Mr. Smith.
Thank you, Mr. Chairman. Space exploration is an investment in our future, often the distant future. It encourages innovation and improves Americans' quality of life. It inspires the next generation to pursue careers in math, engineering, science, and technology. The James Webb Space Telescope, or JWST, is an example of such an investment. The astrophysics community identified the program as the top priority in 2001. The telescope will far surpass in size, power, and capability any previous space-based observatory launched by NASA. JWST is set to orbit nearly 1 million miles from Earth in the Earth-Sun Lagrange point. It is expected to observe the origin of the galaxies, provide insights into the early formation of stars and planets, and characterize exoplanets. The search for exoplanets and Earth-like planets is a relatively new but inspiring area of space exploration. Scientists have discovered hundreds of planets and solar systems in our own galaxy that we never knew existed. By developing and using new telescopes in conjunction with JWST, we may find biosignatures of life on other planets. For example, when examined from a distance, Earth's atmosphere contains large amounts of oxygen. When looked at through a large infrared telescope, like JWST, this biosignature would be detectable. The Transiting Exoplanet Survey Satellite, or TESS, is currently on track to launch in 2017. This telescope will survey the brightest stars close to Earth to find exoplanets. The survey will provide prime targets for JWST and future ground-based and space-based telescopes. TESS has a 2-year planned mission life. It is critical to launch JWST in 2018 so enough overlap exists with the telescopes to maximize the scientific return. As a top priority mission in the 2010 astrophysics survey, the Wide Field Infrared Survey Telescope, or WFIRST, will also contribute to the characterization of exoplanets. If funded properly, it could launch in time to significantly overlap with JWST. This would maximize the scientific return of both telescopes. Each is designed to view different but complementary parts of the infrared spectrum needed to determine the composition of the atmosphere of exoplanets. WFIRST could also have a coronagraph for detecting imaging capabilities. This means the telescope will be able to help determine the chemical composition of a planet. The potential science to be gained from the combined use of these telescopes illustrates why it is important JWST be completed and launched in 2018. However, just as important to being launched on time, JWST must be completed within the congressionally mandated spending caps for the program. If JWST is unable to do this, it affects the ability to build future telescopes like WFIRST. I look forward to hearing how development of the James Webb Space Telescope is progressing. And, Mr. Chairman, before I yield back, let me apologize to members and our witnesses today that I have another committee that is in the process of marking up a bill that I need to go to and will be back, I hope, sometime soon. So while this is the most important hearing in D.C. today, I'll just have to absent myself for a few minutes. So thank you.
Thank you, Mr. Smith.
Yeah, I gotta go. Good old judiciary.
At this time, I'd like to introduce our witnesses. Our first witness today is Dr. John Grunsfeld, Associate Administrator for NASA's Science Mission Directorate. He previously served as Deputy Director of the Space Telescope Science Institute, managing the science program for both Hubble and the James Webb Space Telescope. Dr. Grunsfeld has worked for NASA since 1992 and is a veteran of 5 space shuttle flights. Dr. Grunsfeld received a bachelor's degree in physics from the Massachusetts Institute of Technology and both a master's degree and doctorate in physics from the University of Chicago. Our second witness, Ms. Cristina Chaplain, has been a U.S. Government Accountability Office employee for 23 years and currently serves as Director of Acquisition and Sourcing Management. In this capacity, she is responsible for GAO assessments of military space acquisitions and NASA. She has led reviews of the Space Launch System, the International Space Station, and the James Webb Space Telescope, among others. Prior to her current position, Ms. Chaplain worked with GAO's financial management and information technology teams. She received her bachelor's in international relations from Boston University and a master's degree in journalism from Columbia University. Our third witness is Mr. Jeffrey Grant. Mr. Grant has served in numerous positions within Northrop Grumman and is currently Sector Vice President and General Manager of Space Systems at Northrop Grumman Aerospace Systems. Prior to joining Northrop Grumman, Mr. Grant was Vice President and Chief Technical Officer for Astrolink International, LLC. Before joining the private sector, Mr. Grant served for 21 years in the CIA and the National Reconnaissance Office. Mr. Grant received a Bachelor of Science in Ocean Engineering from the Florida Institute of Technology. I now recognize our ranking member, Ms. Edwards, to introduce our final witness.
Thank you, Mr. Chairman. I'm honored today to introduce Dr. John Mather, who is the Senior Project Scientist on the James Webb Space Telescope and a Senior Astrophysicist in the Observational Cosmology Laboratory at NASA's Goddard Space Flight Center. I'm also proud to say that Dr. Mather is a resident of the 4th Congressional District of Maryland. Seldom does this subcommittee have the privilege of welcoming as a witness a dedicated federal civil servant who is also a Nobel Prize laureate, but today we do. Among his many awards and accomplishments, Dr. Mather, along with George Smoot, received the 2006 Nobel Prize in Physics for work in cementing the Big Bang theory of the universe, an effort characterized by the Nobel Prize Committee as, quote, the starting point for cosmology as a precision science. We welcome Dr. Mather to today's hearing and look forward to his testimony.
Thank you, Ms. Edwards. I'd like to remind our witnesses, please limit your testimony to 5 minutes. Your entire written statement will be included in the record, and at this time, we'll open testimony to Dr. Grunsfeld.
Chairman Palazzo, Ranking Member Edwards, and members of the subcommittee, I'm delighted to appear before you to discuss the status of the James Webb Space Telescope program. Our mission at NASA is to innovate, explore, discover, and inspire. Science at NASA seeks to answer fundamental questions about our universe and our place in it. To view the first stars in the universe, study distant galaxies, probe newborn stars and planetary systems, and measure the composition of the atmospheres of planets around other stars, and to let us study our own outer solar system in detail never before possible, we are building the James Webb Space Telescope. This next great space observatory remains within budget and on track to meet its October 2018 launch date. Built to image and study the faint infrared signals from the earliest stars and galaxies, JWST features a 21.5-foot diameter primary mirror, making this the largest telescope ever constructed for space. JWST will extend our view of the universe, building on the great discoveries made by the Hubble Space Telescope and, as the chairman said, many other observatories with truly transformational exploration capabilities. Since replanning the program nearly 4 years ago, JWST has remained within its yearly budgets. Critical to our success has been adequate funding reserves, enabling the project to address issues as they arise without deferring significant work. The project has done an excellent job doing this and remains on schedule. The FY16 budget request for the James Webb Space Telescope is the same amount called for in the 2011 rebaseline, another indicator that the plan is sound. JWST is a complex observatory operating at cryogenic temperatures, the first of its kind. As a result, we included additional schedule reserve above NASA's usual formula, totaling 13 months of funded schedule reserve. This reserve was distributed throughout the span of the project to allow for resolution of issues as they occur. In nearly 4 years, this reserve has been reduced by only 3 months, so that as of today, we have 10 months of funded schedule reserve. In fact, we have more schedule reserve today than we had planned to at this point, and more than is customary for NASA missions at this stage. This year is an important year for JWST development. We will complete all of the planned work on the Integrated Science Instrument Module. The 18 mirror segments will be mounted to their support structure. The 5 sunshield membranes will be manufactured, and work will continue on the acquisition of parts and integration of the spacecraft bus. After 2015, almost all of the manufacturing will be complete. Our future activities on JWST will involve integration of major hardware elements and testing of those components. As has been noted, there are several technical areas that currently have the greatest attention from management. For example, the mid-infrared instrument requires a special refrigeration unit or cryocooler to cool its detectors to roughly minus 449 degrees Fahrenheit. The design and development of this cryocooler has proven to be quite challenging. Today, 2/3 of the cryocooler hardware has been delivered. The remaining third of the hardware is undergoing final assembly and testing with a planned delivery in 3 months. NASA worked closely with GAO in support of the yearly studies of the JWST program. In response to the latest GAO recommendations, the JWST project initiated a cost-risk analysis of the Northrop Grumman prime contract portion of the JWST program. The results of this analysis showed that as of July 2014, the program budget is sufficient to complete the Northrop tasks on schedule, including accommodation for anticipated risks. The GAO also recommended NASA make changes to our performance evaluation plans for JWST's award fee contracts. In response, NASA has modified its performance evaluation plans for the NASA Northrop and NASA Excellus contracts fee for the award fee determination. The JWST team has been making exceptional progress with significant accomplishments being realized on all of the project elements. Now, nearly 4 years into the replan, the program is within budget and on schedule with adequate reserves for both budget and schedule. We are soon to enter the exciting and challenging integration and test phase. The rigorous cost, schedule, and risk controls that have been employed over the last 4 years give me confidence that we will be ready to launch this ambitious observatory in 2018. The scientific promise of the James Webb Space Telescope is great. The team engaged in its development is world-class in its experience and capabilities. Programs like the James Webb Space Telescope demonstrate to the world that NASA leads the way in expanding the frontiers of human inquiry and innovation. When we build projects like JWST, we push industry to stretch beyond their capabilities, and they rise to the task, strengthening our competitiveness. The success of JWST is the result of a great team working together, including your subcommittee and GAO, and I want to thank you both for your efforts. I'm happy to answer any questions you have about this fantastic observatory. Thank you.
Thank you, Dr. Grunsfeld. I now recognize Ms. Chaplain.
Chairman Palazzo, Ranking Member Edwards, and members of the subcommittee, thank you for inviting me today to discuss the GAO's work on the James Webb Telescope. As you may know, we were mandated to report annually on the program after it experienced a 78% cost increase over its baseline and a 52-month delay. At the time the program was being replanned, there were significant concerns raised about optimistic estimates, low reserves, ineffective oversight, and poor communication. In response to our mandate, we have issued 3 detailed reports on James Webb. Also, we've been assessing James Webb as part of our broader annual assessment of NASA's major projects known as the Quick Look, and I'm happy to say that that report's being released today. This year, we reported that James Webb is still on track with its 2011 cost and schedule baselines. A great deal of progress has been made in developing individual components of the telescope and in overcoming some technical challenges. However, the project is beginning to lose schedule reserve as it has struggled to resolve issues such as workmanship and manufacturing problems with the cryocooler dedicated to the MIRI instrument. We reported that overall schedule reserve had declined to 11 months, and another month was lost since our report was issued. While 10 months is still a lot of time and well within the criteria the program follows, there are still reasons to be concerned about the decline. First, the project faces the very difficult phases of integration and testing. Most space projects encounter problems they did not expect to encounter in this phase. Second, a number of activities have to happen sequentially. The further you go into integration, the less flexibility you have to resolve problems in parallel. Third, there are several elements near the project's critical path which further limits the project's flexibility. The types of technical problems James Webb is experiencing are not unusual for a complex and unique project. They are an inherent aspect of pushing technological, design, and engineering boundaries. What is important when managing such a project is having a good picture of risk, which can shift day to day, and having good tools for mitigating risks as they surface, and knowing how they affect your ultimate cost and schedule goals. NASA has taken an array of actions following the 2011 replan to enable the program to have better insight into risk. However, we reported that NASA had not updated the cost and schedule estimate known as the Joint Confidence Level, or JCL, nor had the contractor updated the risk analyses that underpin the estimate. In conducting our work in 2014, we determined that a current and independent cost risk analysis was needed to provide the Congress with insight into the remaining work on the Northrop Grumman prime contract, the largest and most expensive portion of the work remaining for James Webb. A key reason for this determination was, and continues to be, the significant potential impact that any additional cost growth on James Webb would have on NASA's broader portfolio of science projects. Our preference would have been for NASA to have updated the JCL and to have addressed the fundamental flaws of documents that supported it. We were unable to conduct this analysis, though, because Northrop Grumman did not allow us to conduct anonymous interviews of technical experts without a manager present. In order to collect unbiased data, interviewees must be assured that their opinions on risks and opportunities remain anonymous. This is a key best practice and a fundamental part of our methodology. Unbiased data would have allowed us to provide a credible assessment of risks remaining for the work ahead. Anytime we're denied access to people or documents, we are concerned, since it could be a sign that an entity is afraid of what we will find, but I'll balance that by noting that the program and Northrop have been very candid with us in discussions about risk and in supplying information about risk, and that our relationships have otherwise been very productive. Moreover, in response to our findings, NASA agreed to undertake its own cost risk analysis of the Northrop contract, which was provided to us shortly before the hearing. NASA is also using a new analysis of earned value management data, which should provide the project with additional insight on how current risks affect cost and schedule goals. These analyses look promising, and we look forward to assessing them in our next review. What will be important for NASA is to use the results of these analyses to manage its program and to candidly report on its progress to Congress. Thank you, and I'm happy to answer any questions you have.
Thank you, Ms. Chaplain. I now recognize Mr. Grant.
Chairman Palazzo, Ranking Member Edwards, and distinguished members of the committee, it gives me a great deal of pleasure to appear before you today on behalf of the men and women of Northrop Grumman who are working on the James Webb Space Telescope. And I'm honored to appear with you today with these three other distinguished witnesses. Mr. Chairman, it's been over just 3 years ago since I last appeared before the committee and to discuss the program. And I'm really pleased to report today that the program remains on track, both in terms of schedule and funding for a successful 2018 launch. That is not to say that we've not had challenges. A program of this complexity will invariably be confronted by significant hurdles. We have successfully met the challenges we knew about in 2011, and most of those that have occurred since. The Miri cryocooler, our latest challenge, has proven a difficult one, but one that we continue to make significant progress in completing the last subassembly of that complex cooler. Those members of the committee that were here 3 years ago may recall the path that we laid out to get to a 2018 launch. It was very challenging, but we communicated that it was executable. We have a solid design, as evidenced by the successful spacecraft critical design review that occurred in January of 2014, and a renewed focus and a plan that we are now executing to. The major technological risk reduction work is in fact behind us, and we are now entering the phase of the program where the major risks are in the integration and test phase. Now, despite that, we anticipate that new challenges will emerge, and we recognize the need to do better at addressing these. That is why we continue to incorporate risk reduction activities into the plan to increase our confidence of meeting that launch schedule. For example, The optical telescope Pathfinder will be used to trailblaze the optical testing at the Johnson Space Center in 2017. And the Sunshield full-scale development model will undergo another full-scale deployment test this summer. In addition, we'll be performing early mating of the optical telescope element and the spacecraft bus this summer in advance of the flight mate in 2017. Mr. Chairman, the 2011 rebaseline has been instrumental in our ability to manage challenges with prudent cost and schedule reserve across the fiscal years. The distributed schedule slack has proven crucial in our ability to manage problems as they've occurred within allowable reserves. In fact, all major subsystems have above-plan schedule margin remaining, and we currently are maintaining 10 months of funded slack in our schedule. With less than 4 years to go before launch, this amount of schedule contingency is appropriate for a program of this type and provides adequate contingency for unexpected challenges that may arise. Similarly, we continue to evaluate actions to contain cost, and our financial controls have been designed to ensure contractual discipline to avoid unintended cost. So, I want to ensure the committee at every level that Northrop Grumman remains dedicated to a successful mission overcoming these hurdles. As we move closer to the 2018 launch date, the next few years will be critical. Our immediate focus is finishing the fabrication and assembly of the spacecraft and Sunshield, integrating optics onto the assembled backplane, and completion of the Miri cryocooler. The focus will then shift to integration and testing of the optical telescope element, the integrated science instrument module, and assembling the spacecraft and Sunshield into a single system. This committee's support is essential to keeping the program on cost and on schedule for that 2018 launch. Mr. Chairman, I hope that my pride and enthusiasm in JWST and our partners is evident. From the technicians in the clean room to our CEO, Northrop Grumman remains fully committed to the success of this mission. I want to ensure the committee that we are taking our role seriously and are doing our part to address the technical and programmatic challenges before us. We remain confident in launching in 2018 within the congressionally mandated development cost. I look forward to working with NASA as it leads this amazing effort and with the committee to ensure that this program is a success. So I want to thank you again for asking me to appear before your committee and welcome your questions. Thank you.
Thank you, Mr. Grant. I now recognize Dr. Mather.
Chairman Palazzo, Representative Edwards, members of the subcommittee, thank you for the warm welcome. I'm pleased to appear before you to discuss the scientific mission of the James Webb Space Telescope. I've been a telescope builder all my life. Since I was about 8 years old, I've wanted to know, how did we get here? When I was a kid, nobody really knew, so I became a telescope builder. Quite a few years later, I won a Nobel Prize. But despite our progress, profound questions remain, and I think JWST is the most important project I could be working on. JWST will be the premier observatory of the next decade. To understand JWST's scientific mission, we need to briefly review our current picture of the universe. That picture has been painted almost entirely thanks to work initiated at NASA and made possible by long-standing congressional support. We know today that the universe is nearly 13.8 billion years old. For the first 400,000 years after the Big Bang, the universe had no distinct objects in it and was a hot soup of fundamental particles such as free protons and electrons. Light could not travel very far through that hot soup. Around the 400,000 year mark, the universe went from being opaque to transparent. The afterglow of this era is what we see as the cosmic microwave background. Our NASA team won the Nobel Prize in 2006 for its study of this radiation. The emergence of the first stars probably came when the universe was a few 100 million years old. We think that these first stars were 30 to 300 times as massive as our sun and millions of times as bright, burning for only a few million years before exploding as supernovae. But we've never seen them. Even Hubble can't see them. JWST will let us see them. So why do we need an infrared telescope to see that first light? Imagine light leaving the first stars nearly 13.4 billion years ago and traveling through space and time to reach our telescopes. We're essentially seeing these objects as they were 13.4 billion years ago. But because the universe has been expanding, the light that was emitted by these first stars and galaxies as visible or ultraviolet light actually got shifted to redder wavelengths by the time it reached us. So we need to see it in the infrared. Also, to unravel the birth and early evolution of stars, we need to be able to peer into the hearts of dense and dusty cloud cores where star formation occurs. These regions cannot be observed at visible light wavelengths as the dust makes such regions opaque. JWST's infrared instruments will let us do that. JWST will also look for planets in other solar systems. The first planet outside our solar system was discovered in 1992. Since then, we've come to the realization that planets are in fact quite common. One essential objective of JWST is to observe planets orbiting in the habitable zone of their star, where it is possible for liquid water and perhaps even life to exist. An infrared telescope needs to be cooled down to a lower temperature so it does not emit too much of its own infrared light. To make it cold, we need to put it in deep space where it can be shielded from the heat and light of both Earth and the Sun. It needs to be shielded from the infrared energy produced by its own spacecraft. So JWST will have a tennis court-sized sun shield that will unfold in space. One of JWST's 4 instruments also requires a refrigerator that uses gaseous helium to keep its detectors at about negative 449 degrees Fahrenheit. At this point, I'd like to show you a 1-minute animation of the deployment of the Webb telescope. See if it's going to go. Yes, so it's going. JWST's primary mirror will be composed of 18 hexagonal units made of beryllium, a material light enough that you could pick up one of those units yourself, but which can be machined and polished until it has essentially perfect curvature. If you were to stretch this material the length of the United States, the difference between the peaks and valleys would be about 3 inches. This is an amazing telescope. JWST is an excellent example of what can be done by international partnerships to solve very difficult engineering challenges. The United States is leading a very capable partnership that includes the European and Canadian space agencies. Scientific discoveries know no boundaries, and international cooperation has been very successful for NASA. Beyond its scientific returns, JWST will also be an amazing education tool, as Hubble has been. Nearly every science classroom in the country has posters and teaching materials from Hubble. Every astronomy textbook is illustrated with Hubble pictures. NASA materials are proven to be among the most useful to classroom teachers, and JWST will provide great new material. We are an exceptional country for even dreaming up something like JWST, and we are close to seeing this dream realized. Astronomers will use the telescope to make stunning discoveries and rewrite our textbooks again. Thank you for listening, and I'd be happy to answer any questions you have.
Thank you, Dr. Mather. I thank the witnesses for their testimony. Reminding members that committee rules limit questioning to 5 minutes. The chair will at this point open the round of questions. The chair recognizes himself for 5 minutes. Dr. Grunsfeld, GAO's testimony indicates that the JWST program has 10 months of reserve left, down 1 month from December. The program is now entering the critical integration phase, and all of the subsystems are at risk of becoming the critical path and driving the overall project schedule. This limits flexibility precisely at the time flexibility is most needed. Are you confident that the current plan is robust enough to address the risks facing the program?
Thank you, Chairman, for that question. As I mentioned in my testimony, we have a plan that was assembled at the time of the Joint Confidence Level estimate through the 2011 replan that laid out how we will use all of our schedule reserve. And that is based on a history of similar projects and something that we've shared with the GAO extensively. That burn-down plan assumes that risk is mitigated as we go along the project to solve problems that we discover. And so far, the project has been doing really well on solving problems without using that schedule reserve. And as I mentioned, as a result, we're carrying 10 months of schedule reserve, which is a little bit more than we expected to have at this time. That is the best posture to be in, to have a little bit more schedule reserve than you expect, because we are getting into the test and integration phase where things might pop up that we haven't anticipated with this large complex observatory, especially as we go into the testing at the Johnson Space Center with the optics, starting with the Pathfinder and then the optics in a couple of years. So I'm confident that with 10 months of schedule reserve and the known problems we have now, that we have adequate schedule reserve for the July 2018 launch, so the October 2018 launch.
And this is another question, Dr. Grunsfeld. The President's budget request for fiscal year 16 is for $620 million. This is consistent with the JWST's 2011 replan budget. We are aware that in the original plan, fiscal year 2016 was expected to require less funding because development of instruments and components was anticipated to have been completed. However, with so much integration and testing left to complete, are you confident that the $620 million is still sufficient?
And we have the $620 million in the 16 request, and in the out years, which are notional requests, the same numbers that were in the original replan. And in those numbers, there's a considerable amount of budget reserve. And in the same way as schedule reserve, that budget reserve is there to solve problems. Now, in fiscal year 15, we've allocated a lot of that reserve for known problems through the end of the fiscal year, and we plan ahead with known problems to try and use reserves. So at the present time, the $620 million in the FY16 request we believe is adequate to complete all of the work, as is the funding going out to launch.
Dr. Grunsfeld, and this is also for Dr. Mather if he cares to answer, how would a cost overrun or schedule slip affect other astrophysics projects, science mission directorate programs, or overall NASA priorities? And what would NASA cut to ensure that the JWST stays on schedule?
Well, the first priority is to keep JWST on cost and on budget, on budget and on schedule, and we're working very hard to do that. We have adequate cost reserves and adequate schedule reserve, I believe, to make the October 2018 launch without any kind of a cost overrun. As you know, anytime you have a portfolio of projects and programs, and NASA has quite a few, in the event something overruns, you have to look at what the trade-offs are. I think it's instructive to look at the astrophysics budget historically over many decades, starting with the great observatories and certainly through the last 10 years. And you'll see that if you look at the combination of astrophysics plus James Webb Space Telescope, that budget has been essentially flat. There were very limited transfers, if any, from other programs into James Webb. And so, the cost growth has been contained within this general astrophysics budget. So we're confident that with the budget we have and with the schedule reserve we have, we'll be able to make it on cost and on schedule.
Dr. Mather, would you care to add to that?
I think actually I agree with what he said quite well. Thanks.
So no one wants to really throw out there what NASA would cut to ensure the James Webb Space Telescope stays on schedule. I don't blame you. Probably not smart. Ms. Chaplain, and then I will move on to questions. Are there any preliminary observations on the updated cost risk analysis that NASA performed that you can share? That works.
So we just received the analysis fairly recently. We need to do more in-depth assessments, but on the surface they look pretty good, and NASA indicated it followed not only its own good practices but as GAOs as well, so we look forward to assessing them. We've also looked at the other earned value management analysis that they're employing that takes earned value management a step further and looks at risks integrated with costs and schedule, and can do more predictive things for the program. And on the surface, that looks good as well.
Okay, so you haven't had a chance to definitely dig into it to confirm that they followed NASA's best practices as well as GAO's best practices, but they told you they did, but you're going to dig into it when you have more time.
Yeah, we need to look at the underlying data and talk with them about what they did. There's certain methodological things they probably didn't do that we would have done, like interview the engineers separately and get a good story on what they thought their costs and risks were at that point. But the methodology they did employ is in line with good practices.
And so it also probably be too early to ask you whether or not you recognize any weaknesses in their analysis.
Correct. The only, right now we can't say what the weaknesses are. Correct.
Okay. Well, thank you. At this time, I yield to the ranking member, Ms. Edwards.
Thank you very much, Mr. Chairman, and again, thank you to the witnesses. I want to follow up and looking at the schedule reserve in light of what still needs to be done, particularly as we enter the integration and testing phase. Dr. Grunsfeld, you mentioned, or I think Ms. Chaplain actually mentioned, that there hadn't been a JCL since the 2011. And so my question, and I understand that's a really intensive process, and we don't want to do something that's going to take us away from the game of actually getting the work done. But what is it that we could learn in a JCL or some formation of that gives us the kind of confidence that we need going into this integration and testing phase, that the reserves that are available are sufficient to meet the problems that inevitably will occur. Dr. Grunsfeld and then Ms. Chaplain.
The Joint Confidence Level Assessment is a great tool, and it's based on a probabilistic assessment, so looking at the probabilities of future events when you don't know how long individual parts will take to assemble, how much they'll actually cost. So it's a great tool after the study phase of a mission when we're actually looking at the designs, and we want to predict 3, 4, 5 years out into the future. When you're actually in implementation of a project and you have real hardware and you know what the individual schedules are in great detail, it doesn't make really any sense to do a probabilistic forecast because you already have the information that's contained in those probability distributions. So it's really just an inappropriate tool to use in a very mature project. Now, a cost-risk analysis is a much more sensible thing to do because now you have actual cost, actual risks. You can assign probabilities to those risks, and that's what the cost-risk analysis takes into account and is a best practice by GAO.
So, Ms. Chaplain, do you agree with that?
We would recommend that you update the JCL at any rate. It is a good practice to be especially updating the cost and schedule estimates themselves, and especially because the program, as it's had more experience, could feed that experience into the models. While you did say it's an intensive process, and we recognize that, once you have the model down and everything in place, it's not as difficult to update. But as far as just updating even the cost and schedule pieces of that estimate, it's a good practice to do that on a regular basis.
I guess I just wonder if there are some elements that we already have in place that allow us the luxury of being able to have a greater confidence in the program and that it's going to meet both the cost of the budget and assuming the risks. Dr. Grunsfeld?
Thank you. I think the salient point is that right now we're in the middle of managing a complex project, and there are various timescales on which we do that. To perform a new joint confidence level assessment, we would end up in some number of months with a new estimate, and we could measure against that. But it's kind of like changing the goalpost over time if we get numbers that are different. What we think is much more sensible and as a practical management approach is, and we accepted the cost-risk analysis, but really is to manage the program with the cost, with the reserves, measure how we're doing, and that's why we're using the earned value management, which is a management tool, including some predictive measures, and then we can measure whether we're ahead or behind those predictions. And all of the predictions were based on the original JCL. If we ended up somewhere where we had a very large perturbation, then it would make more sense to go back and say, okay, based on this perturbation adjustment, whatever it is, where we have to re-baseline, then we would definitely do the JCL. I think in the meantime, based on our program guidelines, we'll continue to do the cost-risk analysis and especially continue to manage on the daily, monthly, quarterly basis our earned value management and our standard project management processes.
Thank you. I want to go to Mr. Grant really quickly. So one of the big risks right now is the status of the technical design and of the cryocooler. And so I wonder if you can tell me whether the problems that you were faced are finally behind us. And you indicated in your prepared statement that all of the cooler subsystems have been delivered to Goddard and JPL except one. What subsystem is that, and when will it be shipped to JPL?
Ms. Edwards, the cryocooler program is a very difficult technical challenge. I think in my prepared statement I describe it as operating at 6 degrees Kelvin, very much colder than previous cryocoolers we've built, and it deploys. It's separated from the instrument package by about 30 feet. The mechanical complexities, the heat transfer complexities, the exported force complexities have made this a very challenging job, in fact, more challenging than we anticipated. We've made great progress, though. We've delivered components to Goddard and to JPL, and we're now down to the CCA. It's the cryocooler assembly that is in test today, bake-out testing, and we've got significant performance measurements made that show it meets its spec, which is Great news. And now we're in the final stages of assembly, and we're scheduled to deliver that to JPL in June of this year.
So we'll be asking about that, because I think the problem is that we're gone down now to 10 months of reserve, and the question is how much of the cryo cooler that's been such a problem is going to eat into that reserve to leave enough reserve to stay on budget and on cost for the integration and testing phase. And with that, I think my time is just done. Thanks.
I now recognize Mr. Brooks from Alabama.
Thank you, Mr. Chairman. Dr. Grunsfeld and Dr. Mather, will you please provide examples of how the James Webb Space Telescope, the Stratospheric Observatory for Infrared Astronomy, the Transiting Exoplanet Survey Satellite, or TESS as it's commonly known, will work together in exoplanet research?
Certainly, and I appreciate that question. The Transiting Exoplanet Survey Satellite is very much like the Kepler satellite that has discovered thousands of planets orbiting stars in our galaxy. Kepler has been staring at a region of space that's rather far away from the Earth, and it sees, as the planet goes between us and the stars, a little blink of light. The Transiting Exoplanet Survey Satellite is going to be very similar, except instead of looking at this one distant region of space in the constellation Cygnus, it's going to survey all the nearest stars around our home solar system, around the Earth. And so it's going to give us the address of where there are transiting exoplanets around each of those stars. The advantage we have of a planet that transits, that goes between us and the star, is that we can actually then measure the components of the atmosphere as that starlight goes through the atmosphere of the planet. And so having the locations and types of all of these exoplanets will allow the James Webb Space Telescope to do spectroscopy, or to break the light from those atmospheres into its component colors and allow us to determine, whether there's water vapor in the atmosphere, whether there's characteristics that might indicate even high-altitude clouds, for instance, color changes that would tell us the composition of those atmospheres. So this is an extraordinarily exciting possibility. The Stratospheric Observatory for Infrared Astronomy works in a different wavelength than James Webb Space Telescope. The Hubble Space Telescope operates from the near ultraviolet to the near infrared and encompasses the colors that we see, visible light. The James Webb Space Telescope picks up in that near-infrared and extends out to the mid-infrared, and the SOFIA Observatory extends from the mid-infrared further out. And so there are many objects where we want to do spectroscopy to understand the composition, for instance, of molecular clouds that contain organic materials, very much like what we're made out of. And it'll be the synthesis of the Hubble, the James Webb Space Telescope, the SOFIA Observatory, and also on the ground the ALMA, Atacama Large Millimeter Array, that's really going to be able to put together the picture of how these objects work and how these objects were formed, how they evolved, how organic molecules in these objects formed that eventually may have seeded planets like the Earth before we were around.
Dr. Mather, do you have anything to add?
Yeah, just a few things. One thing to mention about the Stratospheric Observatory is that they can fly frequently with different instruments that are improved as technology improves. And they have already included, there's some extremely high spectral resolution equipment. Spectral resolution separates the colors into over 100,000 different wavelengths. And from that you can determine isotopic compositions and all kinds of remarkable details about the things you're looking at. So it's very complementary to and different from the other observatories we were talking about. So it's not something we could put into the James Webb Telescope.
As y'all may recall, there was an initial problem with the Hubble telescope that required astronauts going up to fix it. Should we encounter a difficulty with the James Webb Space Telescope and the need to repair it, can it be repaired, and if so, how?
I've already volunteered that if there's a problem, you all can send me.
We'll need a spacecraft first. I hope NASA's still
we'll need a
pursuing
spacecraft, and if we have problems, it might be a one-way trip, which you all say I'll deserve.
Well, I prefer the two-way trip.
But the first thing is that we're working extraordinarily hard, and the folks on the project and at Northrop Grumman and all of the contractors, to make sure that we don't need to go to James Webb for servicing. There's an enormous amount of redundancy built in, so for the actuating parts of the James Webb Space Telescope, because it does have to origami unfold like a transformer. So we have dual motors, we have dual sensors, a lot of testing to make sure that everything will deploy as required. While there's no servicing or fixing designed into it, as a relatively small mitigation, we are putting rendezvous sensors on the outside of the spacecraft so that if we ever had to go there for some reason, or if there was some future reason to go, we would be able to align a spacecraft for docking. But otherwise, there's no planned servicing.
So if I understand correctly, the James Webb Space Telescope is designed for docking, but right now we're inhibited because we do not have a vehicle that can get us there. Is that a fair statement?
I wouldn't quite say it's designed for servicing or for docking, but because it has a payload adapter ring, which is how it was attached to, or will be attached to the Ariane 5 rocket, that ring is by definition a place that one could interface with. And we just think it's prudent to put on some sensors, some little stickers essentially with fiducial marks, so that if we ever did have to go there, we'd know how to orient ourselves.
Thank you, Mr. Chairman. I see my time has expired.
I now recognize Mr. Byer.
Thank you, Mr. Chairman, and thank all of you for being with us today. I have some science questions on JWST, and now we have a Nobel Prize-winning physicist here. Dr. Mather, Dr. Grunsfeld said that JWST extends our view of the universe, and you said it was the most important project you could be working on. So 3 quick questions. Will this give us insight into dark energy and dark matter? Second, the Planck epoch, 0 to 10 to negative 43 seconds before the Big Bang. I understand from visiting CERN that we can only get so far back in understanding how close we are to 0. Does this help us get farther back? And finally, the asymmetry of matter and antimatter, the present in the universe, will this help us understand that fundamental asymmetry?
Gosh, such easy questions.
Yeah, it's $8.8 billion.
Yeah, so I'll answer them. For the dark energy, which was discovered based on measurements with the Hubble Space Telescope, we will be able to pursue the same technique, only a lot better, because we can see farther and we can use infrared light to do it. So we know the supernovae, which are used as standard candles, are better candles, better standards measured in the infrared. So number one, yes, we will pursue the dark energy. Dark matter is observed indirectly because it has gravitation. So it bends light, and we've seen that in many places. Sometimes even recently we found a supernova that was seen 4 times in different places as the light was bent 4 different directions around a galaxy in between. So we'll be continuing to pursue that method of measuring the presence of dark matter through its gravitational effects. About the Planck epoch, that's probably outside our territory. That's something that we expect to pursue through measurements of the polarization of the cosmic microwave background radiation. And there is already work underway, and there was a probably false alarm about a year ago that you, I'm sure, saw, where the claims were made about gravitational waves of the early universe. Better measurements will come out soon, I think. We certainly expect them. About the asymmetry of matter and antimatter, I don't know of any measurement that we could make that would affect that question. It's one of the most puzzling mysteries of science, and we know that there's no place in the universe that's like a antimatter galaxy. If there were, we would see an area where the 2 regions were colliding and there would be annihilation energy coming out. So we're pretty sure the whole universe is full of ordinary matter and there isn't any antimatter left except tiny traces. So we'll work on it, but I don't think we're going to answer that question.
Okay. Thank you, Dr. Mather, very much. Dr. Grunsfeld, I was looking at the very sophisticated piece of literature here, our comic book, and it talks about how JWST is going to be in orbit around this theoretical point L2, straight line from the sun to the Earth, L2. It's very cool, but what's at L2 that's going to allow that to orbit around? All my understanding of orbiting is it's based on gravitational forces, or is it just self-correcting engines on the satellite itself?
The L refers to Lagrange, which was a mathematician, and he computed that there would be these points in space where the gravitational force of the Earth and the Sun are balanced such that it's kind of stable, so that if you put something there, it would stay there. And so if you think about the Earth and the Sun, between the Earth and the Sun, there's a point that you can orbit, and an object would get dragged along by the Earth at the same speed as the Earth as it rotates the Sun. We call that the L1 Lagrange point. We just sent the Discover mission there, for instance. The L2 point is on the other side of the Earth, and it's an imaginary point just because there's nothing there. James Webb will be there. But it's gravitationally stable, but it's not perfectly stable. If James Webb were to drift off, we would have to fire some little jets to come back. And so that's that point.
Thank you, Dr. Grunsfeld. And one last question. Mr. Grant, Ms. Chaplain talked about her difficulty doing the anonymous interviews with Northrop Grumman folks without a manager present. We had a lot of discussion here on secret science, on transparency. What was Northrop Grumman's problem with allowing the anonymous interviews or the interviews without managers present?
The issue that we had when this request was made was a request to interview about 30 of our, we call them CAMs, cost account managers, which are reasonably junior employees. They're responsible for small work packages. And I became concerned when the interview technique, it wasn't just anonymous, but isolating our junior employees with a group from GAO. And these are people who are not prepared to come testify before Congress or, in fact, in this kind of environment. And so I had a great fear that this interview technique would result in, frankly, my employees being very, very concerned. This is not how they would normally do their business. And so in my discussions with Ms. Chaplain, I offered, in fact, some alternatives. We're very open to having transparency and full access to the data, but this kind of process to our individual employees concerned me enough that I said, we'll take the management of JWST aside, but I wanted somebody from the functional organization, so a mechanical engineer assigned to the James Webb Space Telescope program would have his functional manager with him in this interview process. So she's accurate in saying no manager, but so I was willing to separate the JWST management from this interview process, but unwilling to send these employees in by themselves. So that's the essence.
Yeah. Thank you, Mr. Chairman.
The chair now recognizes Mr. Johnson.
Thank you, Mr. Chairman. Dr. Grunsfeld and Dr. Mather, how would a cost overrun or schedule slip affect other astrophysics projects, science mission directorate programs, or overall NASA priorities? And you can decide who goes first on that.
Well, Mr. Johnson, thank you for that question. The first part of my answer is that currently we're on budget, on schedule. We have adequate budget reserves and schedule reserves to make our October 2018 launch date.
But that wasn't the question. The question was, how would a cost overrun or schedule slip affect those projects?
Yep. In the event we were to encounter some problem that required, a cost overrun or some kind of slip, as we balance all of our projects and programs, we manage sometimes to an ensemble level, and it's just the realities of the federal budgeting process. So if some project does overrun, then we have to look at future projects typically to delay them or change the phasing of funding to allow to keep the projects that are close to completion on track.
Dr. Mather, you have anything to add to that?
No, he says the same thing I would say.
Okay. Well, do you have a list of what those priorities might be? What would NASA cut to ensure JWST stays on schedule? Do you have any specifics?
So at the moment, in the astrophysics budget and the JWST budget, if you look at the sum of those two, that's approximately the historical level of the NASA astrophysics budget. Mm-hmm. And as the chairman said in his opening remarks, one of the big questions going forward in future budget years is where will the funding for the James Webb Space Telescope go as it ramps down from its main development phases. And NASA has not yet decided on what that future mission might be. Several members have discussed the WFIRST mission, Wide Field Infrared Survey Telescope. This was suggested by the Decadal Survey in Astronomy and Astrophysics in the last round, and is a major priority for astrophysics and something that we're studying in great detail. NASA has not decided to go forward with that. Once we do decide that that's a new mission, and we're examining that, then the launch date for that would be an adjustable parameter based on available budget, technical, and something we would manage to.
Okay, thank you. Ms. Chaplain, what does GAO see as the greatest risk to the JWST program?
At this point, the greatest risk is on the technical side as they first resolve the technical challenges that face them today, like with the cryocooler, and as they get deeper into integration and testing, what problems they might encounter there and how are they going to fix them. The business side is not as much of a risk at this point because they do have a lot of schedule reserve. They do have pretty good tools in place for managing the program. They are pretty rigorous about tracking what's going on. So in our view, the issues now that we'll be intensely focusing on are technical issues as well as risk management issues.
Okay. Back to you again, Ms. Chaplain. You said your annual quick look review of NASA's major programs was just released. So how does JWST compare to other NASA programs in terms of planning, management, performance, and execution?
So it doesn't stack up very well when you consider the cost growth that's already occurred. If you take all the projects together, there's 25.9% cost growth overall on the development side. But if you took James Webb out of that picture, the cost growth for NASA projects would go down to 2.4%. So just its nature, it's a big project on the portfolio. It comprises 33% of the major projects right now. So anything that happens there does have an impact on other programs. And that prior cost growth, though it hasn't come back, is still there kind of overwhelming the other projects at this point.
Okay. All right. Well, thank you. And thank you all for being with us. Mr. Chairman, I'll yield back the remainder of my time.
The chair now recognizes Mr. Babin. Mr. Babin. Just wanted to see if you're going to correct me on that.
Thank you, Mr. Chairman. I'd like to thank the witnesses for being here, reading your bios, very notables, and a while ago in the line of questioning, I think Dr. Grunsfeld actually did 58 hours of spacewalking and EVAs to do some of those Hubble repairs. Is that not the case? Yeah, well, thank you. Thank you for all your distinguished careers. And I appreciate you, too, and congratulations on your Nobel, Dr. Mather. I represent Texas District 36, which has Johnson Space Center in it. And if I'm not mistaken, I think some of this testing, quite a bit of the testing is on JWST is going on at Johnson Space Center, which I'm very proud to represent, and certainly want to see great and big things continue to go and happen at JSC. But in light of all the cost overruns and the problems that we've had, I do have some questions about the project, and I'd like to ask Dr. Grunsfeld and Ms. Chaplain how confident you are that JWST has enough resources now, both in terms of cost and schedule reserves, to execute the commitments that you now have.
I'm very confident that, as of now, we have 10 months of schedule reserve, and we're maintaining adequate budget reserves to meet the October 2018 launch date. There are a number of issues that, I worry about. If you were to say what keeps me awake at night, we're making great progress on the cryocooler. There are a bunch of technical issues. We have a lot of great communication across the whole project now, from daily meetings that the project manager has and communication with us. We have our new program director. We announced that yesterday, Eric Smith. He has daily, weekly, monthly meetings. We meet routinely with GAO to talk about our progress. But there's some things that we just don't control. And for instance, one of those is that we have 3 major tests at the Johnson Space Center in that great Chamber A and we're starting some of the testing now on the Pathfinder. And if any of the members have an opportunity to go there, I highly recommend that you see this. This is where we tested the Apollo Command Module. It's enormous, and that reflects the great size of the James Webb Space Telescope. But one of my worries has been, that we have 3, multiple-month test periods at the Johnson Space Center, and having lived there for 18 years, I've had to leave my home occasionally for hurricanes. What happens if we're testing during a hurricane? And so I've interrogated the project on what is our mitigation, and I've been down to the Johnson Space Center several times talking to the engineers and the operators of that chamber, and they have great plans in place. And the James Webb Space Telescope can actually survive through a hurricane without significant interruption to the testing. So they've assured me that even those kind of risks are incorporated into our modeling to make the October 2018 launch date. So I'm very confident that we have a very sound plan.
That's great. Thank you. And how about Ms. Chaplain? Did you want to add anything to that?
So 10 months of reserve is a long time, and the cost reserve is very healthy, and I don't often get to testify on programs with that kind of luxury in terms of reserve, but it's also a very complicated program, and its test program itself is 7 years. Integration and testing is 7 years long, and the thing to keep in mind with 10 months of reserve is you need certain amounts of time for each phase of testing, so you can only apply certain amounts of reserves with each phase. So if a major problem does come up, you don't necessarily have 10 whole months to fix it without disrupting other parts of the schedule. So we're still concerned about schedule, but they are in a healthy position at this point.
Thank you. Thank you very much. One other question, and this would be for Dr. Grunsfeld. You actually, both of you and Ms. Chaplain addressed this to a certain extent a while ago, but does NASA share GAO's concern about the amount of schedule risk remaining in the program?
I would say absolutely. In terms of, my personality, but also that of Robert Lightfoot, our Associate Administrator, Charlie Bolden, we're all very concerned about the risks and the schedule reserve in the sense that we are for every single program we manage. I generally would not say that I'm comfortable with any of our projects because that's just my personality, and that's one of the ways that we do so well in managing our projects and programs is to stay a little bit uncomfortable and keeps us on edge. I am confident, but I wouldn't ever say comfortable until we launch. Okay. The best place for a spacecraft like James Webb Space Telescope is in space.
Amen. Thank you very much, all of you, and thank you, Mr. Chairman.
Thank you, Mr. Babin. The chair now recognizes Mr. Posey.
Thank you, Mr. Chairman. I really appreciate the incredibly wonderful and exciting things that you do and that the James Webb Space Telescope will do for us. Obviously, I have a serious interest in gaining and maintaining public support for our space programs. There's a lot of misconception, as you all know. Poll after poll has shown people think we spend as much as 25% of our budget on our space program when it's less than 0.5%, and they hear you're spending over $600 million more on the space telescope, and they say, what's in it for me? I mean, how do you articulate to the average American family who may have no idea what the telescope does, how it's going to benefit them?
Well, let me start and then maybe ask John Mather to comment additionally. I mentioned in my testimony that one of the great things we do in this country is challenge industry to do hard things in the name of science, in the name of fundamental questions about our universe. And when we challenge industry to do that, it forces them to grow. It increases our competitiveness. It also attracts the best and brightest minds to come to the U.S. and to rise in the U.S. to help solve these problems, to study astronomy, to study astrophysics, so perhaps they can win a Nobel Prize in the future.
But that may be a little bit over the head of the average taxpayer, is what I'm talking about.
Yep.
This booklet you have is really excellent material for those of us who already have an interest in it, and for a teacher who has a chance to maybe impart that hunger into students. But I'm just wondering, how we quantified, how it benefits the national security, the economic stability, or the survival of the species. That we make that connection when we're talking about this expensive product, which is very necessary for our future, I think, but that we haven't really managed to connect with the average American about the importance.
There are some circles where I can talk about the contributions of the James Webb Space Telescope. It's the largest space telescope we've ever built, segmented optics, the first time we will have flown a large space telescope with segmented optics to, say, national security. The average person that I talk to when I'm giving an astronaut talk, they don't have an appreciation of that. But I'm glad you mentioned, the effect on teachers. The Hubble Space Telescope, for instance, reaches more than 500,000 teachers a year, 6 million students a year, and is viewed by 9 million people.
I
and
got
those
that.
kind
I got
of
that.
applications
I heard that. I got that.
Are,
I love
are
that.
important.
But how do we connect with the average American family who's worrying about their job, who's worried about feeding their family, being able to finance their kids in education? How can we explain to them that spending the money on this telescope, which I think is very important, obviously, should be that important to them?
I think if you talk about NASA, generally my experience has been that people understand why we invest in NASA. We are investing in America's future. We're investing in future technology. We're investing in innovation. And most people have the same questions that we have as scientists that drove us to become scientists about, where did we come from? Where are we going? Are we alone in the universe? And that NASA is providing the tools to answer those questions. Those fundamental questions are the same for everybody. And when you can talk about that we're only spending, less than 1% of our federal investment on investing in the future, I think people do resonate with that.
Doctor?
I certainly agree that that's why we do it and why the public loves us to do it. I used to ride the subway in New York City. I'd be sitting there with my astronomy book, and people would say, "What is that? Tell me about it. Where did we come from?" The public is really interested in this. And when they're not working to support their families, they say, "Where did I come from? Are we the only ones here in this entire universe or not?" And I think we're getting towards being able to answer their questions. People just have a deep passion to know where did we come from, our genealogy, our history, everything about how we got here to this amazing committee room here in Washington, D.C. They want to know, how did that happen? So I think we should help them answer that question.
Thank you.
Yield for just a minute.
Yes, I'll yield.
Mr. Posey, perhaps Dr. Grunfeld might want to respond to your question by answering us how the JWST program has enabled a number of improvements in measuring human eyes and the diagnosis of ocular diseases and improved surgery for eyes as a connection to people. Dr. Grunsfeld?
I'd love to talk about that. Thank you very much. Sometimes what we call spin-offs are a bit tangential, but in this case, and Dr. Mather mentioned it, I was in a very early James Webb Space Telescope meeting where they were talking about the smoothness of the mirrors. And, I started scribbling in my notebook to figure out, what if you stretched one of those mirrors, a single 1.5 meter beryllium mirror, to the size of the United States? How big would the bumps be? And he already told you the average bumps would only be about 3 inches tall if you stretch those mirrors to the size of the United States. This is an astonishingly smooth surface. In order to generate that amazingly smooth surface, the engineers at Ball Aerospace had to come up, with algorithms and techniques of measuring what the shape of the mirror is to that extremely fine detail. And that's actually, those tools have already been incorporated into the kind of techniques and tools that ophthalmologists use to measure the shape of the human eyeball in order for the laser surgery and other techniques, to correct human vision. And so there's many, many examples of these kind of things.
Well, that was kind of my point. Listen, we mostly sell steak in space, and Winn-Dixie and Publix and all the supermarkets, but they don't advertise steak. They advertise sizzle. And so, we're all interested in the steak, but the public needs to know a little bit more of the sizzle, and so, if somebody asks about James, well, decrease the probability of you going blind because of ocular disease by 50%. Well, that's something the average guy can identify with, rather than, we talk so often in platitudes. We want to know where we came from, where we're going to go. We realize that ultimately, someday, humanity will have to leave this planet or perish. And we know that. But it's so far away that the average family doesn't want to worry about that right now. Let 50,000 generations from now worry about that. But we have to make our contribution to getting us off this planet when the time comes as we go. But I find that it's so important to quantify space direct benefits to people to gain that public support. Like I said, they want some of the sizzle. The meat doesn't interest them right now. They want the sizzle, like the supermarkets sell.
If the chairman would indulge me, I have one more small story.
The chairman will indulge you.
Thank you. I was doing an astronaut visit, so I'm in a blue flight suit, to a small company outside of Chicago called Numerical Precision, and they're a machine shop. And we were walking through, and one of the engineers, technicians, showed me a part that he was building that he was very proud of. And it was a little circular ring. And I don't know why, but I recognized it. And it was odd. Most of their work is defense work, or much of it. And so I started asking him about it. And this is a company that had made tools that I used on the Hubble Space Telescope, and they were very proud of that, and I was there to thank them. And so I asked him, what program is that for? And he said, I don't know. And his manager said, let me look. And he comes back and says, some NASA program. And I think, okay, that's piqued my interest. Maybe I know this part. And it turns out it was a part for the James Webb Space Telescope. The story the plant manager had told me is that this part was very hard for them to make. And it's made by a special technique involving machine tools that only the United States has been able to refine. And he said that by building this difficult part for the James Webb Space Telescope, they developed new techniques, and they had actually, by using those techniques, been able to attract a lot of business. And their biggest problem was not the new business, but the ability to hire young people to run these machine tools. And he said that by working on NASA projects is one of his biggest draws, to be able to bring in young technicians. And these are people with high school graduates who like to use computers. Yeah. Now, I have a son who's soon to be a high school graduate, and he spends a lot of time on computers. A little bit different than we expect, but he's very talented now at controlling computers for things like computer games. And he's now also the head of his robotics team in high school, which is a similar sort of things. So we have plenty of young students who would be great at machining, which is now a very exciting field. And the James Webb Space Telescope helped contribute this company to be able to hire people. And I certainly think jobs are what a lot of people think about, and these are very high-paying jobs.
The chair now recognizes Mr. Lucas.
Thank you, Mr. Chairman. And I appreciate the panel being here and their insights. And if we could for a moment, slide perhaps back to a few more nuts and bolts. The challenge, I think, has been expressed rather clearly by all of you that James Webb is so unique or so different than Hubble in that whatever we put up has to work the first time. Those of us who were paying attention 25 years ago remember the initial trauma after the launch of Hubble, the miraculous repair job and the wondrous things accomplished from there, and all of the service work and improvements and additions made. But this is a different creature. This is a one-time shot. So I listened very closely to Director Chaplain's comments about the 7 years of testing and the various components and this and that and the other. Let's talk for a moment about this cryo-cooler business. Because my understanding is we have to keep James Webb at an incredibly cool temperature to function, and that we are, in effect, creating technology as we go here, or developing techniques to make this possible. Discuss for just a moment how complicated that particular issue, for instance, is. Whoever would care to answer the question. Thank you, Mr. Grant.
I'll be happy to. At Northrop Grumman Aerospace Systems, we've been building space-qualified cryo-coolers now for many, many years, and they have flown successfully on many missions. both scientific and meteorological. And so we build these cryocoolers that operate at very low frequencies or very low vibrations, so they don't disturb the imaging system that they're attached to, and they have to operate very efficiently, so that you have very, very efficient conversion of solar power to the mechanical compressor power. The unique elements of the Miri cooler are we have to do those things in addition to cooling far colder than we have put a space-qualified cooler at before. Coolers we build and operate today operate at about 70 degrees Kelvin. This one operates at 6 degrees Kelvin. And the whole observatory is operating at about, in the optics, at about 40 degrees Kelvin. So the instrument is cooler than the optical background temperature.
And reminding us, of course, that 0 Kelvin's absolute zero.
Correct. All molecular motion stops. Yeah, it's very cold. So it has to operate very cold, and it has to operate very efficiently. It has to export very low export forces, and it has to operate with the cooler separated from the cold head assembly on the instrument module by about 30 feet. So there's an array of technical complexities in this cooler that made it far more difficult than coolers we have built before. I would say the good news is, well, the program started, and there wasn't even going to be a cooler on it. It was going to be a doer, a solid block of gas that would be frozen and then sublimate over time to cool the instrument. That would work, but it was very heavy and also runs out of gas. So the cooler has the possibility of operating, in fact, as some of ours have, for decades. So we went to the cryocooler design in about 2006, if I recall, and since that time, we've made significant progress. Just this past year, we got data that confirms its flight performance, so we know it gets cold enough, it's efficient, and has low exported forces. So we're at the point now in this development where most of the sub-assemblies have been delivered, and this one last one is in its final stages of integration and test. So it's been a very long, tough, challenging road for us to be on, but as we speak today, we're very close to the last delivery.
Mr. Mather, thinking back to 20-some years ago when all of the issues were addressed on Hubble and it became kind of a wow moment for most of the human race that cared, all goes well, all the targets are met, all the flight operations are smooth, we park it way out there in the proper place, everything switches on. We're going to have that magnitude of a wow moment again?
I certainly expect so. I wouldn't be doing this if I didn't think so. By the way, I wanted to add one thing to his testimony that only one of the instruments requires that cooler. The telescope and the other 3 instruments cool down by themselves, just because they're hidden behind the big umbrella. So there's a risk, but it's not a huge risk if there's any problem with that. So we're certainly going to point the telescope at beautiful things and get great pictures. We expect amazing discoveries ranging from the first stars and galaxies to the formation of stars and planets close to home in places like that beautiful Eagle Nebula. We certainly want to see those little exoplanets like Earth, if there are any, orbiting around stars way out there, see if they're wet, like do they have oceans. So there's this huge array of wonderful questions to answer, and I think nature may just cooperate and give us answers. So that's our plan. And I think it'll be very exciting times for us.
So as they'd say in the coffee shops back home, if something's winking at us, we'll know it.
Yes.
Thank you, gentlemen and ladies. I appreciate it very much. Thank you, Mr. Chairman.
Thank you, Mr. Lucas. We enjoy talking about the nuts and bolts as much as Mr. Posey's steak and sizzle. I want to thank the witnesses for their testimony and the members for their questions. The record will remain open for 2 weeks for additional written comments and written questions from members. This hearing is adjourned.
That's a great